So do you have any questions?
Yes, sir. This one was in ISI 2014 sample paper.
Okay.
So it goes like this, sir. There is a frog.
Okay. Uh,
So there's a frog on a lotus leaf that has N petals.
mhm.
So if we can infer that the petals are like in like a circular arrangement, and what it's
Mhm.
given that the frog jumps using the following rule. In the first jump, it skips one leaf. Second jump skips two leaves. Third jump skips two petals. Sorry. Third jump skips three petals, like that.
Okay. So the rule is
Yeah,
ith
eighth jump.
uh, s- skips I petals.
Yes.
Okay.
And now they've given the information that uh, so it starts jumping, and eventually it covers all the petals. So we have to prove that n cannot be odd. Yes.
Hmm.
So first thing I did, I took smaller cases for like
Hmm.
3, 5, 4, and all those.
Right.
And I noticed that in the ith jump, it'll be in the ith triangular number mod n. That petal it'll be on. So if we
Oh.
label the petals 1, 2, 3, 4 up to n,
Hmm.
yes, sir. And suppose starting point is 1.
Hmm.
So first jump, it will be in third, third petal.
Right. Yeah.
So I plus 1th triangular number, sorry.
Right. So after the ith jump, so let's write that,
Yes.
and that is quite clear.
Yes, sir.
Ith jump, uh, position position is I plus 1th triangular number. So that would be what,
Yes.
like I plus 1, I plus 2 by
By
mod n.
mod n. Yes, sir.
Yes. And it's if you're in an exam, you can just write a proof of this by induction or something.
Yeah, by induction,
Yeah.
we can write.
Hmm. Okay.
Oh, 1 second, sir. Suppose if we put 1 in I, 2, 2. Okay, yeah, it works. It works. Yes, sir.
Hmm.
So now I was thinking, instead of that n, we can put 2k plus 1 to get some kind of contradiction.
Hmm.
Well, now from here, I don't know what to do, sir. But one idea I had was trying to see what will happen in the 2k jump.
Right. Okay. Okay. Let's see. 1 second. So okay. So in the 2k jump, it will be here
Yes. Mod 2k plus 1.
mod 2k plus 1.
But then clearly that'll be 0 because multiple of 2k plus 1.
Uh, so
Now
yeah. So
0, I think it comes back to that position, I think.
yes. Wait. So is this is mod n correct, or should it be mod n plus 1?
Um, I mod. So I think mod n should be correct. So we can take for example 5. We can check with an example 5 petals.
Mm-hmm.
So then first jump, zeroth jump it'll be at 1.
Mm-hmm.
Then it'll go to 3. Then it'll go to 6 mod 5, which is 1 as required.
Right. And after that,
After that 10 mod 5, which should be right, 10 mod 5 will come back to 1 because it'll skip 5 steps, right, sir? So it'll skip 2, 3, 4, 5.
no, no, wait. It should skip 3 petals, right? So it should come to 5.
Okay, 1 second. First jump, it skipped 1 second. Yeah, it should skip 3 petals. Sorry. Yes, sir.
Yeah,
It should come back to 5.
yeah.
Right,
But
right.
then if you do mod n, then you never come back to 5. So
But you get 0 in that case.
yes, yeah. So you have to interpret this as 0.
Yeah. Or we can start numbering from 0 to n minus 1. Then we'll have n petals.
Yes, right. Or if you do mod n plus 1, then also you get the correct thing.
Yes, sir. Then also you get the correct.
Wait, is that correct? So you get 3,
Yeah.
and then you skip 2, so you do 1. So if it's 3, then
Plus 3.
no. So why is it wait? Mm,
Oh,
yeah, right. You come to 6, and then no. So mod n plus 1 does not work, right?
yes. Yeah, it doesn't work.
It doesn't work.
So
You just call this
I think
0.
we 0 to n minus 1. Yes, sir.
Uh, okay, yeah, or I just call it 1 to keep 1 to. Okay, maybe it's the same thing. Yes, let's call it 0 to n minus,
Yes.
and 2k.
Yeah. So
But
2k,
now,
2k. Yes, sir.
right? But now the
Right.
positioning is now the formula may be incorrect.
We have to check that once more because first zeroth jump it'll be on 0 only.
Hmm.
First jump it will be on, this time it'll be on 2 mod n. 2 mod 2k plus 1.
Hmm.
Yes, sir. I think I no normal ith triangular number.
Yes.
Yes.
So now,
So so if we put I equal to 1, we're getting 1 into 2 by 2, 1 mod n, but it's on the second position, not first petal.
no, but the petal number is 1, right? Petal number
No,
is
no,
1.
no. So after one jump, it'll be on petal number 2 because it's skipping the first petal.
Oh, yeah. So
So
then
the
it was the same formula.
yeah, I think same formula. We could try that.
No.
So what 0 0 first jump it will go to 2 mod 2k plus 1. Second jump it will skip 3 4 and it'll go to 5 mod 2k plus 1. So I think triangular number minus 1.
Yeah, right. Correct.
Yes, sir.
Yeah. Just give me a minute. I'll just come back. So,
Yes. Yeah, two. రావచ్చు.
All right, so finally we
Yes.
have the formula. Now,
Formula, yes.
so if there are n petals, then it is like this. Okay.
Yes, sir. So I think we'll expand it and say that -1.
One second.
So
So so if there are if there are 2k plus 1 petals, then it will be this, but the numbering will be
yes,
till 2k, and
yeah,
in this case we are able to visit everything. Okay. I mean, okay. So we want to say that we cannot visit everything. So
yes, sir. If there are odd, so some petal must be skipped.
hmm. So let us think about it. So if you have tried the smaller cases, you would know which petal was skipped.
Yes, sir. I first few small cases, what I was getting was that the petal numbered 1 will always get skipped. But then that is wrong.
Why?
So because I think what I took was as you take bigger examples, what will happen in that first petal will get covered. So first petal won't get skipped. Then I thought of looking at suppose we have 2k plus 1, then 2k plus 2 by 2, that petal will get skipped. I thought that
Hmm.
I still haven't verified, sir, but that might be right. But this first petal, it'll get covered
It is getting covered.
using bigger values. Yes. So this formula, we can just reduce it into I into I plus 3 mod 2k plus 1. Just expanding and all that.
I into I plus 3.
Mod 2k plus 1.
So we can forget the denominator
By 2, sir, by 2.
by 2, right? But we can also forget the denominator, right?
Uh, why is that, sir?
So let's say you have this. So this is, no, one second. So if it is this modulo 2,
Yes.
mm, so this is, so is it
Yes.
factorized? So let me check it. So I
Yes,
square,
sir. I factorized it.
okay. 2 minus 2. Right, correct.
Yes, sir. So now, since we have like this kind of formula, so
Mhm.
maybe we can put I is equal to 2k and see what will happen. Or I is equal to 2k plus 1, 2k minus 1, something like that.
Right, let's do that.
So I think first we could try 2k minus 1.
Hmm. 2k
Yes, by
minus 1. So I equal to 2k minus 1. Okay.
it's giving us this.
Yeah, so then you
So
come back to 0.
yeah, you come back to zeros, I think.
Hmm. So in the 2k
So
minus 1 jump.
so how will it be zero, sir? Like if you expand or like if you check.
Or was it not
Uh
0?
I'm not sure, sir. Sir, we're getting 2k minus 1 times 2k plus 2 divided by 2.
Oh, okay, because it's 2k minus 1. Sorry, yeah. No, no, no. So
Yes,
it doesn't come to 0. It goes to k plus 1. 2k
k
minus
plus
1
1
times k plus 1. So
mod.
can we check what that is? 2k minus 1 times k plus 1.
Yes, sir. So if we expand that out, you get 2k squared plus 2k minus k minus 1. So there'll be 2k squared plus k minus 1.
But then when you simplify that, 2k, 1 minute.
Yes.
That is something nice, right? It's minus 1
Yes, sir.
or
Minus 1.
2k. It is 2k. Right? That is 2k.
Yes, sir.
Yeah. So it does go to the 2kth petal.
Sir, but this is we're taking mod 2k plus 1.
So that's what I did. That's what I did. Right?
Oh, okay, sir.
Let's see.
Oh, 1 second, sir. I didn't understand the. So if we expand it, it'll be
No, so I'm not
2k.
expanding it like that. That can be
Oh,
done,
okay.
but what I'm saying is that this 2k minus 1, I write it as like this.
Okay, okay. 2k plus 1 minus. Okay.
Yeah. And then it is 2k minus 2, right? And then I
Yes,
write
sir.
it like this, and then I forget this. So it is minus
Okay,
1,
okay.
and
Yes,
minus
sir.
1 is 2k, right? So it's in the 2kth petal. So 2kth petal can also be reached. That's one thing we learn.
Yes, sir. 2kth petal can be reached in the 2kth jump.
Yeah, the 2kth jump. But
2k minus 1, sorry, sir. 2k minus 1 jump.
jump, yeah. So we get the 2kth petal.
So now what if we put 2k in the formula, sir? We'll get
Hmm.
or or what if we put something that gives us directly 2k plus 1? So something like 2k
Okay,
minus 2.
that is right, but let us think a little bit.
Yes, sir.
We want to say that all the petals cannot be reached, right?
Yes, sir.
So notice one thing here, that when you run I from, like, let's see what is the extent of this. Like when you run I from 1, then you'll make I equal to 2
Yes, sir.
and so
You'll
on. You get, and then you make I equal to 2k plus 1. So when you make I equal to 2k plus 1, you actually go to 0.
0. Yes, sir.
So that's 0. So this is
Because
also erased.
mod.
Yeah. But uh, no, it's 2k plus 4 by 2. But notice that when you put I equal to 2k plus 2, you again
Okay.
get something that you already got.
2k plus 2.
Yes. Right?
Okay. Yes, sir.
So my point is that in the 2k plus 2th jump,
Yes, sir.
you do not go to a new place.
You come back to 0. Yes, sir.
Whether you come back to 0, is that
Oh, okay, okay, okay. So some petal that you've already visited. So it repeats after that. Yes, sir.
yes,
Because mod is like cyclic.
it is mod that works, right? Exactly, because the
Yes.
jump may tell you that, oh, this is now you're going to take a longer jump and so on, right? but
Ah. But then the
mod will take care of it. So you can see it either way. So from the formula itself, right, when you put 2k plus 2, it is like putting 1.
Yes, sir.
So
It
you
is
can
like
see,
putting on.
yeah, so you can see it in any way you want. But the point is now that we have to only look at this list.
Yes, sir. These numbers.
These numbers, and there are 2k plus 1 numbers.
Correct, sir. Yes.
Yeah. Now to show that they are not all from 1 to n or 1 to 2k plus 1, what can be
Yes,
the
sir.
strategy? So this is the set of numbers, maybe mod 2k plus 1.
Oh, sir, I think I got it, sir.
Hmm. What is
So
it?
we have so we have 2k plus 1 numbers in the list, and we have 2k plus 1 petals. So each number should be distinct here,
Yes. And then
but
is it distinct?
it's not distinct, so that's what I am getting.
Yeah.
To verify that, I think there will be at least one jump where you will come back to where you're starting. Like
Yes.
suppose you're on the fifth petal, like you reach the fifth petal, then you'll come back to the fifth petal. That's what I've observed. So like in the cases, so now I think we can prove it using the formula.
Yes. So you have to show that two numbers will repeat, and you are in fact saying that you will come back to the same.
Same number, sir. So suppose I think if you take to 2k minus 2, so let's see what will happen, sir.
Yeah.
Instead of I.
Let me not erase these. These are there. Okay. 2k minus 2.
Yes, sir. Yes, sir. 2k minus 2.
2k minus 2 is jump, you mean?
Yes, sir. 2k plus 1. Yes, sir. So this will be zeroth petal, no, sir?
Hmm.
But then
Yes.
2k plus 1th jump is also zeroth petal.
Yes. So that's it. Done.
So that's it. We're done. Yes, sir. Yes, sir. Yeah.
Yeah. It was
This was a
very.
nice question.
Yeah.
Yes, sir.
So this is
So some
2k.
petal must be skipped.
Yes. And in fact, you have told which two numbers repeat. Means
Yeah.
which two terms in the
Yes.
sequence repeat. You've actually told the exact answer. Yeah.
Yes, sir. Yes. Got it, sir.
Nice. So it is really on a level, it is really like saying that a quadratic equation has two distinct solutions for a like
Yeah.
yeah, so there is some number, let's say 0, which for which there are two solutions, which means two values of I give the same value of 0.
Yes, sir.
It is that.
So similar in spirit. Yes, sir.
Yes, right. Yeah.
So I think this was B. I think this was B8, sir. I think last question on the test.
Nice. But it is not
This one.
difficult. It is not difficult,
Yes, sir.
right? You
It
have to
is not
just
difficult. Yes, sir.
notice this mod thing. Yeah. And in fact, maybe I can make one small comment is that if you
Yes, sir.
look at if you look at this list, right, and if you
Yes, sir.
multiply this list by 2, multiply every number by 2, then this list that you get below, this is a
Yes, sir.
permutation of the list above,
Yes, sir.
because
So
2
what a
is Hmm?
permutation as in?
Yes. So what I'm saying is that if the above list has distinct numbers, then these are also
Yes, sir.
distinct.
Correct, correct. Yes, sir.
So maybe I will say this in a separate way. So suppose you have, um, no, so yeah, permutation is a wrong word. What I want to say is that let us see that there are k
Yes, sir.
k
Okay.
distinct numbers, okay, mod sum n, right?
Yes.
Now if you multiply each of them by a, and again you are
Yes, sir.
considering them mod n,
Mod
then
n. Yes, sir.
these are also distinct if mod n, then
Yes,
these are
sir.
also distinct if a and n are co-prime.
Okay.
Then
If a,
these are,
correct, correct. If a and co-prime. Yes, sir.
you see that,
Yes, sir. Yes, sir.
right? Yeah. And that is why in this problem, in fact, one can ignore the two.
Okay.
So all this number
That,
theoretic, yeah, and then it becomes
yeah,
even
yeah, yeah.
easier. Then it just like
Easier to
saying,
see. Yes, sir.
yeah, means even if one doesn't see that both this lead to zero, one can just check. Okay, let's try to find for which is this possible, and then one can get the value of ij for which these are
Yes.
equal mod 2k plus 1. Right, so it's
Yes,
not
sir.
it's
Got it.
easy. I think you can generalize this question, show that
Okay.
n cannot uh, have a factor of 2.
Show that n cannot have a factor of 2. Okay.
So you can try this later.
Yes, I'll try. I'll try it, sir.
Yeah. Meaning that not just odd, right? It cannot even have any 2 as a factor.
So
Okay.
it should not have, yeah, 2 power k in its prime factorization.
Yes. Yeah. And also prove that, okay, let me put it,
Yes.
since you have said 2 power k, let me put it
Yes.
like this. All the petals if and only if n is equal to 2 power k.
Okay. Yes, sir.
All right. So try this. We will discuss that next time maybe. All
Okay.
right.
Yes. I'll try this.
Let us move on.
Yes, I had one more question. I just wanted to verify my solution, sir.
Mm-hmm.
I got the answer. So find all natural numbers n
Mm-hmm.
such that n into n minus 101
Mm-hmm.
is a perfect square.
Okay. So
So
how do you?
some m squared. First, what I tried was I distributed the k and all those, but I got weird solutions, so I abandoned that. Then what I did was normally I expanded n squared minus 101 n minus k squared is equal to 0.
Mm-hmm. Right.
Then you put n is equal to 101 plus or minus.
Okay.
No, sir, plus or minus to the left. Uh, The quadratic formula I use, sir.
Okay. You're kind of solving for it. Okay. You're solving.
Yes, I'm solving for n to see what kind of constraints we would have.
Mm-hmm. No.
Yes, sir.
Minus. No. This plus. Yeah.
Plus it'll become. So 101 squared minus plus 4k squared. Sir.
Plus 4k square. Yeah.
Yes, 101 squared minus 4ac. So that would become plus 4k squared. So now this thing in the radical, that should also be a perfect square.
Yes. Yeah.
It can't be 0 because otherwise 101 by 2 not a natural number. So
Mm-hmm.
this thing we're getting it as m squared, some m squared. So now what I did, sir, was we know that 101 is prime.
Mm-hmm.
So what I did was 101 squared is equal to m squared minus 2k whole squared.
Yes. Right.
Right. So now a difference of squares, m plus 2k, m minus 2k
Mm-hmm.
is equal to 101 into 101. So now we have a few possibilities.
Mm-hmm.
101 is prime. So we did the prime factorization of 101 square. So m minus 2k, m plus 2k, they both can individually be 101.
Mm-hmm. Yes.
So, but if we take that, we'll get 2m is equal to 202,
Mm-hmm. Then
or
2k.
m is
Then
equal to
k is 0.
k 0. Yes, yes.
That's
M is
solution.
equal to 101.
Yes. And then you can similarly try all the other possibilities. There are some
Yes,
5
I tried
possibilities.
all the other
Yeah.
5 possibilities.
It
You
will.
get only one solution, sir.
Yes. So that's easy.
It's
No.
correct, sir.
Wait. Yeah, it is correct. But why do you get only one solution? So this 1 and 101 square. This should also give you a
Huh,
solution.
this one. This is the solution that works, sir.
No, but n equal to 101 is not wrong, right? That's also a solution.
Oh, but they want k squared to be the square of a non-negative. I mean, what is that? Non-zero positive natural
Oh,
number.
non-zero,
That's why
huh?
the
Yeah,
non-zero. Yes, sir.
you're correct. That's yes,
Yes,
that's
sir.
right. Okay.
So this was also, I think, ISI, sir, but part A most probably.
This one was easy. Yeah, the usual.
Yes, sir.
Basically, the discriminant has to be a perfect square. If it has to have
Discriminant has to be a
integer
perfect square.
solution,
Yes.
yeah, that's
Yes, sir.
certainly a necessary condition. Some and yeah, that is no, but
Yes,
there is
sir.
just one small thing that you may have to uh,
Yes, sir.
is that when you find m and k, you should make
Yes,
sure
sir.
that this is an integer.
Yes, sir. That yeah, I verified that as well,
Yeah,
sir.
but in this case, you see, if this is a rational number, this will always be integer because the numerator will
Yes.
be even. So actually, you don't have to check.
This in this
I-
case we don't have to check.
In this case, you
Yes, sir.
don't have to check because this is odd. Yeah. All right, so this is easy.
Yes, sir.
Okay. So you have more questions?
Uh, I have one more similar one, sir. I did it, but I don't think there's any mistake in it, sir. Like, but it was an interesting question.
Hmm.
Suppose n is a natural number
Mm-hmm.
such that 8n plus 1 is a perfect square.
Okay.
So first question is, can n be even? N is equal to 6 works. So that is done.
Okay. That is done.
Second question was, can 2n be a perfect square?
Okay.
2n equal to m square. Then if we just put that in the first equation, we'll get 4m squared plus 1 is k squared.
Mm-hmm.
So k squared minus 2m whole squared is 1.
K square. Right. Yeah. So this should also be possible,
Yes, sir.
or yeah, you'll find some. No, this only one. One seems very small.
One's very small for this to happen. You'll get 0. So I think 0 or something like that you'll get.
Hmm.
Which of course they don't allow natural 0 as a solution. So we get 2n cannot be a perfect square.
Okay. All right.
If
That's
unless n is 2n cannot be a perfect square. That's what we get, sir.
all right. But then this is
Yes, sir.
okay.
Apart from these, over the week, I tried a few geometry questions, sir.
Mm-hmm.
Uh, I got one, but it has quite a lengthy method. So can you tell me if there's a shorter method?
Yes. So let us try that. So I'll do one thing.
Yes, sir.
As last time, I'll end the
Yeah,
meeting and
yes,
launch it. Yeah. Then you join.
yes,
Then
yes.
we discuss the job.